Welcome. This is a recorded version of a talk that I gave recently at the MODELS'17 conference in connection with my paper there, Bidirectional Transformations in the Large. I'll try to give it more or less as I gave it at the conference, perhaps slightly more slowly. Bidirectional transformations is much too much of a mouthful, and so we normally abbreviate that to BOOKS, BX. So let me start by saying what books are. Fundamentally, they are a means of maintaining consistency between models. So a BOOKS has to say both what consistency relation ought to hold between the models that are being worked on in parallel, and also how that consistency relation should be restored when it is lost as a result of changes being made to one or more models. And so the vision we have is that in order to facilitate efficient, agile development, we've separated the concerns of software design so that there are lots of models and they're all being worked on in parallel, and periodically they're being brought into consistency by means of these books. Now we can worry about what periodically should mean, but at the very least we would like to be sure that we can, when we want to, get a fully consistent set of all the models. So here it is in a picture. This picture now appears in all my talks, and it's usually titled something like Software Development in 2050. So the idea here is that we've distributed the software decisions that have to be made to different groups of experts, and each group of experts is working with a model which shows all and only the information that they need. So perhaps we've got two different groups of users who use a system in different ways up here, each working with a model that's relevant to their concerns. And down here, judging by the Greek letters, we've probably got a group of mathematically inclined people, perhaps they're safety engineers who are concerned with the safety properties of the system. The interesting part here is that we've got a bunch of coloured wires, and these are the books. So the idea is that the books' job is to take all the models and bring them into consistency by reading and writing the models as appropriate, so that there will be some deployable software which is consistent with all the models, in other words, which incorporates all the decisions that have been taken by the different stakeholders. And it will be necessary not only to read these models but also to write them, because it won't necessarily be the case that for every collection of a model from here, a model from here and a model from here, there could even exist deployable software consistent with all those models. Sometimes decisions taken by one group will be in contradiction with decisions taken by another group, and some kind of reconciliation process will be required. That's the job of the books. So a very interesting open question for our community is, what do really good languages for writing those wires, for writing the books, look like? Now, you might not be happy with my cartoon, or you might not be willing to wait until 2050. So let's momentarily look at a real example. And this is part of the AutoSAR megamodel. It's a small part of the AutoSAR megamodel. The trouble is, you can't really read it, and if I explained it in full, either here or in the paper, my time on my page limit would be up before I'd said anything else. And so what I want you to take out of this slide is just that there are lots of models, I'm only showing a few of them here, and that they are typically related by overlaps relations. That's what these overlapping circles indicate, that the information represented in one model overlaps with the information represented in another model. In other words, each model will capture some information that's not recorded in the other, but there is some non-trivial consistency relation that has to hold ultimately between those models. Also interesting to note is that, at least in this snippet, all these relationships are binary. They relate exactly to models, not more than two models, although we have a network of those binary relations. So as a compromise, in the paper, and to some extent in this talk, I'm going to use this small megamodel. So we'll call it a megamodel because it represents a collection of models and the relationships between them. Let's look at the relationships in turn. So the idea is that the relationship between the UML metamodel and the UML model is going to be our standard conformance relation. The UML metamodel is going to be consistent with a given UML model if and only if the model conforms to the metamodel. The relationship between the code and the model is going to be our standard round-tripping relationship, and as usual we expect there to be some information in the UML model that's not reflected directly in the code, use cases for example, and some information in the code that's not reflected directly in the model, maybe the detail of how methods work. This relationship down here that I've indicated with this T-shape relation is somewhat more interesting. So here we have a relationship that involves some code and some tests and also a safety model. And what I want you to have in mind in this tiny example is the idea that the basic relationship between the code and the tests is that the code is going to be consistent with the tests, a set of JUnit tests or whatever it might be, if and only if the tests pass the code. But actually it's going to be a little bit more complicated than just an if and only if relationship like that. Because what we're going to say perhaps is that there might or might not be a more stringent relationship than that. Perhaps we're going to say the safety model will record, among other things, whether or not this is a safety critical system. And if it's a safety critical system, then it's not enough for the code to pass the tests. We might also require that the tests cover the code in some appropriate sense. So we've got a ternary relationship between the code, the tests, and the safety model. So that's really the focus of this paper. All too often in the books field, papers, and I'm a prime offender here, begin something like, a bidirectional transformation is a means of maintaining consistency between two or more information sources. And then they're written entirely on the assumption that there are exactly two information sources. We say something like, for ease of presentation, we consider here the case of two. So the question is, do we, as a community, in order to realise that vision we have of separation of concerns between however many teams of domain experts there might be, need to devote more effort than we have done hitherto to considering multiary books? And multiary is a word that I use to represent n-ary where we're not limiting ourselves to any one particular n. So the case of bidirectional transformations that maintain consistency between an arbitrary number of information sources. Or alternatively, is it a needless complication for us to consider multiary binary relations, multiary bidirectional transformations? For example, if we devote effort in our bidirectional transformation languages to allowing the language to represent the relationship between more than two models, are we unnecessarily complicating our book's language, or are we doing something that's important in order to realise the transformative potential of bidirectional transformations? So the first part of my talk I'm going to look at that expressiveness issue. Now the first thing we might do is to think about how we can express ternary or multiary in general relationships between more than two model sets in terms of the conjunction of consistency relations on pairs of those model sets. So here's a tiny mathematical example which shows the limitations of that idea. So to read this, the idea is that we've got three different model sets. So we've got A models, of which I'm showing two examples, A primed and A, as being models in that model set, and B models and C models. So the idea is that we've got our three different sets of experts, three different groups of experts. One group of experts works with an A model, and one of the decisions they might take is the correct model for this system A or A primed? Another group of experts works with B models, and they might be deciding between B and B primed. And another group of experts works with a C model, and they're deciding between C and C primed. And obviously this is a tiny, tiny mathematical example, and usually our groups of experts will be deciding between an unbounded set of models, not just two. But this will suffice to make the point. And so the idea here is that we are given, via the process of requirements engineering, a ternary relationship which captures the consistency between these models. So our customer tells us that the triple of models A, B and C primed is consistent. And they also tell us perhaps that the triple of models A, B primed and C is consistent. And they tell us that the triple of models A primed, B and C is consistent. And then they say, and that's all, those are the only triples of models that should be considered to be consistent in this particular development. And our task is to say, can we define a collection of binary bidirectional transformations, binary consistency relations between pairs of these model sets, such that the existence of a triangle in our given ternary relationship is logically equivalent to the existence of all three edges of that triangle in these binary relations that we are to construct. So we would like to say the customer has given us a ternary relation in which A prime BC is a consistent triple, but we are going to construct three binary consistency relations in which A primed and B are consistent, B and C are consistent, and A primed and C are consistent, and the existence of all those three pairs in the appropriate binary relations is going to be equivalent to the existence of the ternary relation we were given. Now, unfortunately, we can't do that, and you can probably already see why, but let me highlight it. It's because we're going to get emergent triangles, however we do that. So in this particular case, if we were given those three triangles that the customer said were all the triples that were consistent, however we construct our binary relations, we're going to be forced to include A and B in the binary relation between the model sets A and the model sets B, because that was an edge of one of the triangles we were given. It was an edge of this triangle we were given, A, B and C primed. And similarly, we're going to be forced to include the edge between B and C in the BC binary relation, and we're going to be forced to include the AC edge in our binary relation between the model sets A and the model set C. And since the way we set up the problem, the idea was that the existence of a triangle in the ternary relation we were given was supposed to be logically equivalent to the existence of all three of the edges, if we're forced into a situation where all three of these edges of the black triangle have to exist, that means we're forced into accepting that triple A, B and C as a consistent triple in the ternary relation. But it isn't. It wasn't one of those that the customer told us they wanted to be consistent. Here it is in symbols, for those of you who prefer it that way. The key point here is that we don't control the requirements. So what we can say is that a multiary relation R, this is our given set of requirements, is going to be binary definable if and only if we can in fact find a collection of binary relations on the pairs of model sets which is logically equivalent to the original multiary relation in the sense that we saw. And the example that we just saw shows that not all relations are binary definable. The relation that included the three coloured triangles, but not the one I ended up outlining in black, is not binary definable because of the fact that we would be forced to include those three edges of the triangle in the binary relations when we tried to construct a set of binary relations that would binary define our original multi-relation. And those inclusions would force the inclusion of the triple ABC in the multi-relation, and it's not there. That's a contradiction. And let me say at this point that if you're thinking of a different way to relate a collection of binary relations on pairs of model sets with multiary relations on the set of all the model sets from the one I've got on this slide, you're almost certainly thinking of the other one which is discussed in the paper, and quite cutely there's a Galois connection between the two notions, and you can see more about that in the paper, but I'm not going to spend more time on that in this talk. So, oh dear, if we limit ourselves to considering only binary bidirectional transformations, we do indeed lose expressiveness. But let's not give up too fast. We'll now look very briefly at two possible solutions and at their drawbacks, and then at some counter-argument to the potential drawbacks in order to explore what the pros and cons of this limitation might be. So our first attempt at a solution comes from the constraint satisfaction problem domain, where a closely related problem has long been studied, and there's quite a literature on ways to do this. So what they know in that field is that if you have a constraint network, which is to say a set of variables where each variable can take any one of a certain number of values, and you have constraints on those variables, then if you have a non-binary constraint network, you can translate it into an equivalent binary constraint network by using additional variables. Now in our case, adding additional variables amounts to add an extra model set. So we might say, okay, so we know that we want to have a certain collection of models because we have a certain collection of stakeholders and we want to provide each stakeholder with a model that records all and only the information they need. But maybe we have to set up our project differently. Maybe we have to add an extra team and an extra model that they'll work with, and perhaps that will allow us to get away with using only binary relationships between these teams. Now, there's a whole literature in the CSP field of different ways to do this and the pros and cons of each, and that's briefly discussed in the paper. But the extreme case is to say what we'll do is we'll add a single model set, and the values of that model set, the values of the variable, the models in that model set, will simply be all consistent tuples of your original models. So in the case of our tiny example there, because we had 3 consistent triangles, we'll add a new model set, call it capital M, and the models in that model set will each be one of those triples, one of those consistent triples. And that's exactly the same as adding our Multiary consistency relation as a model set in its own right. And then we connect that new model set to the original model sets by binary books that just say that they agree on the relevant model. So we'll say that the binary relation between our original model set capital A and our newly added model set capital M should record, for example, that little a is consistent with the triple ABC primed because of the fact that little a occurs in both of those 2 places. And then we can observe, if we wish, that those binary relations do indeed binary define a relation on that product of 4 model sets that, when we restrict it to the 3 model sets that we were originally interested in, A, B and C, gives us exactly the Multiary relation that we first thought of. Okay, so in that sense we can indeed express our original Multiary relation in terms of binary relations by adding an extra model set. So are we happy? We absolutely are not happy. That solution was not one. If we knew how to construct all consistent tuples of our model sets in the first place, we wouldn't be modelling. That would completely defeat the purpose. Oh dear. Well, maybe, however, it might still be a useful idea. So, for example, perhaps that would be a decent way to get rid of the odd ternary relation that might turn up in a situation where most of the relationships are binary. So let's park that for a moment and think about a second possible solution. So the second thing we might do is to try refining the consistency relation that we were given. So we started off by saying we were going to be given, as part of the requirements, a Multiary relation between our different model sets, and we were going to try to find a collection of binary consistency relations that expressed exactly that. But maybe that was unreasonable. Maybe it would suffice to express something that implies the Multiary relation that we were given, not something that's actually logically equivalent to it. So we might say that fixing some binary consistency relations is an architectural decision, like so many others that get taken early in development and, in effect, limit the solution space available to us. So we're quite used to the idea that we might gather some requirements that could be met either by using an object-oriented design or by using functional programming, say, and at an early stage we decide that we're going to use object orientation. And by making that decision, we rule out some parts of the solution space that would, in fact, in terms of the original requirements, have been perfectly satisfactory, and we're not upset by that at all. Well, some of us aren't. So to formalise that, what we would be saying would be that we would move from this relationship that I put up a few slides ago, which is to say that we would consider a Multiary relation to be binary definable if we can find a collection of binary relations that are logically equivalent to it in that sense. And we would replace that notion by a weaker notion of a Multiary relation being binary implementable, provided that we can find a collection of binary relations which imply the multiary relation that we were interested in. In other words, we can find some binary relations that are sufficient to satisfy the requirements, even if they're not necessary to satisfy the requirements. For example, in the little model code tests example that I gave a few slides ago, this might amount to saying, well, okay, what we'll do is we'll say we will always maintain the coverage criterion between code and tests, even if it isn't strictly required, and at least that way we'll know that we will satisfy the multiary relation that we were given between those three model sets. So, does this allow us to handle a wider class of multiary consistency relations by re-expressing them using binaries? Well, yes, it does, because all relations are binary implementable. Now, you may be ahead of me. You may be saying that's completely trivially true, because all you have to do is to select an unsatisfiable collection of binary relationships, and that will be sufficient to demonstrate that your multiary relation is binary implementable. Now, in fact, something not quite so trivial is also true, and you should see the paper for details of that. Okay, so we can refine the consistency relation as a second possible solution to enabling us to work only in terms of binary relations. Are we happy? Well, maybe. Although you always can implement your multiary consistency relation via a set of binary relations, it doesn't follow that you can necessarily find yourself a nice set of binary relations that are good to develop to, in the sense that your teams who are working in your different model sets will be satisfied by the effect of working with those binary relations. In the extreme case, it may be that your binary relations are back-derived from a single consistent tuple. In other words, they might restrict your development space too much. There's an example in the paper which you might like to look at, and there's a lot more we can say about this. Fundamentally, this is an empirical question, I think. In practice, will we actually be restricting our development scope too much? We'll need to experiment with this in order to find that out. At the large scale, the examples I know themselves feel rather artificial, and that goes for the one in the paper as well. So it may be that this is a problem that doesn't really show up. It would be a diversion from this paper to discuss it, but certainly when you consider things at a lower level, you can come up with cases where the examples don't feel so artificial, so it may be a real problem. But I think probably the crucial counter here is that people find it much easier to work with binary consistency relations without making mistakes than they find it to work with multiary consistency relations. And one of the reviewers of this paper said something to this effect, and I think this is absolutely right. There's no point in having a wonderfully expressive books language if people can't actually use it to express the things that they think they're expressing. And that's, I think, the best argument for saying maybe, even if it's not always ideal, we might be happy to restrict ourselves to working with binary consistency relations via binary implementability. This slide is really for people who are already familiar with books, and it amounts to saying that a downside of restricting the development more tightly than the original requirements did is that you might falsely reject what is actually a good solution. So the scenario that we might have here is that we might say we have our original multiary consistency relation, and we have a collection of binary relations that implement that. And what happens is this: the models are being worked on independently, and at some point all the expert groups are happy with their models, and so they press the check consistency button. And we might say it happens that all the models right now do in fact satisfy the original multiary consistency relation, but they might not satisfy the binary consistency relations we actually were using. Now at that point, if we're really serious that we're using the binary consistency relations, we are nevertheless going to go and modify the models so that they do satisfy all those binary consistency relations. But if people get to hear about the fact that actually their models were perfectly fine as they were, according to the original Multiary relation, they might not be happy about that. And that amounts to a failure of Hippocraticness, for those of you who know what that term means. Now, we might counter that by saying, meh, but that kind of thing happens all the time. You make a decision early on, you happen on a solution that would have been okay but contradicts a decision that's already been made, and we live with that. And the other counter you might make is to say that actually you should be restoring consistency as you go along, and that will very much reduce the chance that this actually happens. But more could be thought about in that direction. To summarise this little exploration, the answer to the question of do we need our world-beating bidirectional transformation language to be written so as to allow us the syntax, for example, to express multi-Ary consistency relations, depends on our assumptions. If we insist on fixing both the set of models and the consistency definition precisely, we're not willing to bend on either of those points, then yes we do, because otherwise we'll lose consistency. But if we're prepared either to add extra models or to refine the consistency relation, then no, we can manage with binary consistency relations only. So, for the rest of this talk, let us suppose that, so far as consistency is concerned, we settle on using a collection of binary bidirectional transformations that must all be satisfied. In other words, they binary define some multi-Ary consistency relation, and we decide that the multi-Ary consistency relation that they define is good enough for the purposes of our development. Let's go on now and think about consistency restoration. So, we've got some model sets. So the points in each of these models sets are entire models. This might be a set of UML models, this might be a set of suites of JUnit tests, this might be a set of collections of Java code, whatever it might be. And what we're saying is that we've got some binary consistency relations between these sets of models. And in principle, of course, we might have to consider the complete graph on our model sets. For any pair of models, we might have to ask ourselves, is that pair of models consistent? However, in practice, in some cases we'll find that there aren't any special consistency requirements between a model pair. In other words, the corresponding binary consistency relation is universal. Any pair of models are consistent as far as that particular relationship is concerned, and then we needn't bother drawing those consistency relations because they're just always true. And so we end up with a network like this, in which the nodes are sets of models and the lines are binary consistency relationships between those sets. Now an instance is going to be one model drawn from each of these sets, so a tuple of models that might or might not be consistent. And what we say is that that tuple is consistent if and only if each pair drawn from the tuple is consistent according to these binary consistency relations. If a given tuple is not consistent, then the question will arise of how we change some or all elements of the tuple so as to restore consistency. So we might, in principle, modify all the models in the tuple, but it's often less confusing to know that some of the models in the tuple will not in fact be changed. Now this might happen for a number of reasons. It might be that for some of these models you are not even allowed to modify that particular model. For example, it might be, say, that our set D of models is the set of meta models for the modelling language we're dealing with, and so the element of this set that we're currently working with, our little d and capital D, might actually currently be the UML meta model. And however much we might like to modify the UML meta model in order to restore consistency to our tuple, we're not allowed to do that. It's not realistically a helpful thing to do. Alternatively, it might be that a different reason for not wanting to modify a model in a given model set might be that right now we don't want to do that. Maybe the customer just signed off on this model and we don't want to have to go back to them and say, actually we just modified it, would you like to sign off on that again? So fundamentally what we're doing by saying that some of the models in our tuple will be authoritative, and that's what I indicate by a solid background in the corresponding model set, is we are just cutting down the space of possible things we might do in order to restore consistency to the tuple. And we're further going to cut it down by saying that just as we've restricted our notion of consistency to be expressed via the notion of consistency that's given by the binary consistency relations inherent in each of the binary books, we are going to also limit our mechanism for restoring consistency to the tuple to being that given by the binary books' consistency restoration functions. And so for purposes of this talk, the consistency restoration problem says, given some models, some of them authoritative, connected by some binary books, we want to find a sequence of applications of the binary books' consistency restoration functions that restores all of those consistency relations. So here are some of the key concepts from the paper, and I'll illustrate some of these by example in a moment rather than going through them now. So having decided what we want, we immediately see that we can't always have it. So not all authority instances have resolutions. So here's the most obvious possible example. If we have a model little a from model set big A, which we're not allowed to change, and we have a model little c from model set C, which we're not allowed to change, and we are asked to find a little b from model set B such that that little b will be consistent both with A according to binary relation R and with C according to binary relation S, then we won't be able to do so if there isn't one. So if there is no B which is consistent with A according to R and consistent with C according to S, if the intersection of those sets is empty, then we are absolutely out of luck. We will not be able to do that. People present at MODELS'17 heard a nice talk by Davide Di Ruscio at EXI about doing this in a practical sense in one particular setting, and he discussed the need to send give up signals to the user in cases like this and several of the other cases that I'm going to explore mathematically now. Slightly more interestingly, not all authority instances that in principle have resolutions, in other words, have tuples that are indeed consistent according to all the binary consistency relations, are actually resolvable. In other words, there aren't always sequences of applications of the consistency restoration functions that will actually get us to the consistent tuple. So here's a tiny little example to illustrate that. Now in this picture, the idea is that all the lines here are indicating consistent pairs, pairs which are consistent according to the appropriate binary consistency relation, and the solid lines are indicating our actual starting tuple. So we're going to start with a model little a in the A set, and that's authoritative, we're not allowed to change it, and so I'm not illustrating any other models in that set since we aren't allowed to use them anyway. And it is connected to a model B1 in the B set, and it's consistent with it, and it's also connected to a model C1 in the C set, and it's consistent with it, but B1 and C1 are not consistent. That's why they're not connected with a line. However, we do have these various consistent pairs in the BC consistency relation, and similarly we've got this alternative consistent pair in the AC relation there. Now you can see that there is in fact a triangle in this setup. If we were able to get ourselves to the triple A, B1, C2, then all of those binary consistency relations would be satisfied. However, in this rather abbreviated set of information about the binary consistency relations, the idea here is that we have constructed an example where you can see that you can't get to that consistent triple. So now, given that these are going to be binary books and they're going to be Hippocratic as usual, in other words, if you try to restore consistency on a pair such as A and B1 that are already consistent, the consistency restoration function will not change anything. The only choice we have to make here is whether we're going to apply T forwards, in other words, keep B1 the same and modify the C model to bring it into to be consistent with B1, or whether we're going to apply T backwards, in other words keep C1, our current model from the C set, fixed, and modify our B model in order to bring that into consistency with it. Let's consider the possibility of applying T forward. So if we apply T forward on the current set of models, which is B1 and C1, then what this is telling us is that that's going to give us as a result the model C3. Okay, so we're going to say if we ask the T forward consistency relation to modify C1 so as to bring it into consistency with B1, what it's going to give us is C3, which indeed, as you see, is consistent with B1. So we could do that, but unfortunately that wouldn't bring us into a consistent tuple, because C3 is now not consistent with A. Oh dear. What could we do? The only thing we can do, given that A is authoritative, is now to apply the S forward consistency restoration function, and that, as we see, is going to give us C1. In other words, what that's going to do is when we say please restore consistency between A and C3 by modifying C3 to something at which will be consistent with A, it's going to take us right back to where we started, to C1. Okay. Now similarly, you'll find if we take the alternative route of choosing the T backward function, that too will take us in a loop that will not bring us into this triple of consistent models, even though that exists. So there is a resolution, but it's not resolvable. We can't get there using the consistency restoration functions of the binary books. Now the next thing we might ask ourselves is, well, okay, suppose that there is a network in which it is resolvable, so there is a solution and we can get there using the consistency restoration functions of the binary books. Will we have a unique solution? In other words, whatever choices we make, and there will in general be a choice of in what order to apply the consistency restoration functions, will we always get to the same final tuple of consistent models? Well, no, we won't always. In fact, hardly ever will this be the case. It's quite easy to construct counterexamples, and you can see the paper for a bit more information about that. Sometimes a choice of direction, like our choice of T forward and T backward on the previous slide, in our case neither of those got us to a solution at all, but it might be that they both got us to solutions, but to different solutions. The other thing that might happen is that we might have a choice of order in which to apply the consistency restoration functions, and that also might lead us to different solutions, if it leads us to a solution at all. Some networks are indeed confluent, and now let's spend a few slides exploring the situation under which that actually happens. So we can capture what we want by looking at this fragment from a diagram where the issue is going to arise. So suppose that we have consistency restoration functions that will modify C in the light of A, or will modify C in the light of B. What we would like is to say it doesn't matter in what order whether we apply R and then S or S and then R, because we'll get the same answer whatever we do, regardless of where we start, and that is what that expression at the bottom of the slide says. Well, that's very nice. It's a nice thing to have. Does it ever hold? Well, actually, yes, it does. Now, the simplest possible case is where actually C was a Cartesian product. So you could say that model C that we were looking at, actually any model in the model set C really comprises two independent sets of information. There's some information that is relevant to the A model, which the consistency restoration function R may have to look at and modify, and then there's an independent collection of information in the model which is relevant to B, which will be looked at and modified by S. If that holds, it's easy to see that we will indeed get non-interference, and if we get enough non-interference, and also a condition I'm not going to talk about in this talk, then we will get confluence, and that's very nice. But more interestingly, you can also get non-interference in cases where the effective model space is rather small. In other words, the space over which we are universally quantifying, in that condition for non-interference is rather small, and that arises, for example, in the case of handling changes for a rather stable metamodel. Now, earlier on in the MODELS'17 conference, Benoit Combe gave a talk in which one of the things he remarked was that in 83% of cases that he'd looked at, a UML model which was stated to conform to a particular version of the UML metamodel actually conformed to any of a rather wide version of UML metamodels that they checked it against. And this supports the idea that we will very often be able to say for all plausible changes in future to the UML metamodel, the only change we'll have to make to a UML model in order to restore consistency with that metamodel is that one line at the top of the XMI file that says this is the URI of the metamodel I have to conform to. And it's quite easy to see that that then is quite likely to be non-interfering with other changes that you might have to make to the UML model in order to restore other kinds of consistency with other models. So going back to our tiny megamodel example, it's quite plausible that for a given way of making this precise, the consistency restoration functions between the code and the model and the metamodel and the model might well be non-interfering. It's probably the case that these two consistency restoration functions will not be non-interfering because they are likely to affect overlapping pieces of information about the code. So armed with the non-interference tool, in this paper we pick a tiny bit of low-hanging fruit in the paper and we show how you sometimes can get confluence in networks of models like those we're going to consider. And I should confess that I'm eliding some stuff, so you are very likely to think tree-woods, but in fact not all trees are confluent because of some things that I'm eliding, but never let that be. So the first thing we do is we add a supersource, which is going to act as the root of our near tree. And the next thing we do in the paper is to say we're going to identify some set of models in our megamodel such that the consistency restoration functions that target a model in that set are all non-interfering, as we just discussed. And such that if we then made a copy of each of those models, one for each of the targeting consistency restoration functions, the resulting graph would be a tree. So in this case you can see if we took two copies of the model, one to be attached to this consistency restoration function and one to be attached to that consistency restoration function, we would have a tree with root the supersource. Now in that case, given the stuff I'm eliding, we can prove that we get resolvability and that we get confluence. So you get the basic idea. A little bit on related work, although obviously see the paper for more detail on this. The point I want to make here is that some of the work that we're building on here that is related takes a gives up some control over how consistency restoration happens. So it, for example, might use a program repair view, or this is quite interesting work that merges models by making a sensible choice of which pair of models to merge first. And in both of those cases, what you're doing is you are limiting the predictability of failure, but also lowering the probability overall of failure. And so you pays your money and you takes your choices there. And there's also some interesting work in particular formalisms that looks at some of the ways of proceeding there. So there are lots of different avenues to explore, and I think this is going to be a really interesting area in future years. So some of the work that I personally plan to do in future are listed on this slide. The most interesting thing to discuss here, I think, is a thing we didn't really mention here, which is to say we've talked as though the entire instance from the whole network is going to conveniently stay still while we go around applying consistency restoration functions on it to bring the whole tuple into consistency. Now, in any practical situation, in fact, while we're busy applying binary consistency restoration functions in one part of the network, we can reasonably expect that other parts of that network are actually changing under our feet as those teams continue to work. So we're going to have some kind of distributed notion of consistency restoration, and I think there are some really interesting possibilities to do some interesting things there, perhaps related to some earlier work that I did on partial consistency restoration, in which instead of saying all or nothing, we restore consistency between models, we talk about increasing the level of consistency between models. Now, I said I thought there was a whole lot of interesting work to be done in future years on this, and so perhaps you won't be surprised that there's a Dargstuhl coming up here. It's being organised by Eckhard Kindler with a little bit of help from Anthony Cleve and Vadim Zaitsev and me. It's probably going to be in December 2018. Invitations will be out shortly. Space is very limited, as always at Dargstuhl workshops, so I'm afraid I can't make a blanket offer to invite people who would like to come, but we would particularly like to hear about any early career researchers to whom this is relevant, because those are often harder to identify than people who've been around for a while. So if that might be you, or if that might be somebody in your research group, please do send me an email and I will do my best to invite them. And that's all I wanted to say, and if anybody has questions or comments or funding opportunities, you can't ask in the session, but you could send me an email. Thank you very much.